Okay, this section is about limits, and it's a fairly long section, so I'm going to break this video up into several pieces. Limits are the building block of major calculus ideas, and at a certain point, we'll understand those calculus ideas well enough that we're not going to be speaking about limits directly as we apply calculus, but limits are doing work behind the scenes. And in order for us to understand these key ideas, we need to at least understand a limit. The good news is we don't need to learn the super nitty-gritty technical definition. We just need to be comfortable with the idea. So let's motivate this with an example. Let's look at this function, f of x. It's a rational function. The numerator is x squared plus x minus 6, and the denominator is x minus 2. So what happens if we try to compute f of 2? So just pause and tell me what happens when we try to compute f of 2. All right, so I'll plug this in. So I have 2 squared plus 2 minus 6 over 2 minus 2, which is 0 over 0. And here's the thing. The 0 in the numerator is not really a problem, but we know we can't divide by 0. So what we're noticing here is that f of 2 is undefined. It has no value. It does not exist. There are a few different ways of saying this. So f of 2 just doesn't exist. It would involve dividing by 0. Okay, but now let's take a step back and say, what do we think f of 2 is supposed to be? Technically speaking, it's not. It doesn't exist. It doesn't have a value. But maybe that's just a technicality. Maybe we feel like it's supposed to have a value and we're just missing something. And I do want you to understand this is not a crazy idea. As we move forward, we're going to look at certain calculations and we'll want to do a calculation where we realize, oh, when I try to do this calculation, I'm getting division by 0. But I know this is a meaningful calculation that measures something I want to know. So maybe if I wiggle around a little bit, I can say, well, it looked like I got that something doesn't exist, but actually I know what the answer is supposed to be some other way. Right? So maybe we should, what do you think this could be? So just pause and think about some ideas as to how can we get a feeling of what we feel like this is supposed to be, even though it is technically undefined. All right, so maybe you came up with some ideas. I'm going to show you a few ways of addressing this. So one is we could just gather numerical data. So using a calculator or some other tool, we could evaluate what is f of x when x is extremely close to 2. We know that f of 2 doesn't have a value, but maybe when we're really, really close to 2, that will tell us something worthwhile. And close to 2 here doesn't mean a number like 3 or 2.5 or 1.5 or even 1.9. Close to 2 you really want to think of as like very, very, very close to 2. So I'm actually going to make a little table of values. You could do this by just plugging them in one at a time on your calculator. And here, I'll make this a little bit cleaner. So if I plug in 1.997, my answer is 4.997. Got that from a calculator. If x is 1.998, I get 4.998. Here I get 4.999. Here, we know this is undefined. And if I keep going with these others, all of these x values are very close to 2. And I might notice there's a pattern in these y values that I'm getting. So this is one way of making sense of what we feel like it's supposed to be. We'll gather numerical data. We could also look at a graph. Let's look at this graph and try to figure out what's happening in that graph near x equals 2. So I already have this ready to go in Desmos. Here's our graph. Just looks like a line. Now, technically speaking, if we zoomed in really, really close, right, so I think it'll show this for us. If you see, when we put in 2, it does recognize that it's undefined there. We have a tiny little hole. Right? The hole's so small that you can't really see it unless you go in specifically at that point. There is a hole right around here. But near this point, we see it in the graph and we see it with these numbers. That I could zoom in and zoom in and zoom in. What I'm noticing is my x values, if they're my x value is in this neighborhood around x equals 2. My y value is in the neighborhood around y equals 5. What our graph looks like, and I'll just draw a really rough version of this. Oops. Here's x equals 2, here's y equals 5. There's technically a hole there, but it just kind of looked like a line. Right? The graph here is a line with a hole in it. But that does give us a sense of what's supposed to be here, right? So maybe this isn't supposed to have a hole. And I know I'm being vague here, but the idea is we got something that's undefined, but it doesn't feel all that bad. The graph is a line with just a microscopic hole in it. In either of these cases, what we notice is if our x value is close to 2, our y value is close to 5. We can see that by specifically just listing numbers. We can see that with the graph. Here are some points on the graph where x is close to 2 and y is close to 5. And moreover, it's not just about close to. What we'll notice is as x gets closer and closer to 2, y gets closer and closer to 5. So it's not just about being nearby, but there's kind of a pattern. If x is getting really, really close to 2, then y is getting really, really close to 5. And we can summarize what we're seeing with the limit. So here is how we could say this. So first of all, let me just tell you how to pronounce this. This thing on the left, we would say the limit of f of x as x approaches 2. This arrow, x arrow 2, is communicating x is getting close to 2. X is moving towards 2. The verb we use is approach. Or sometimes people switch the word order here and they say the limit as x approaches 2 of f of x. What this whole thing means is the numerical value f of x is very close to when x is very close to 2. That's what this highlighted thing means. It means what is the numerical value that y, that f of x is very, very close to, assuming x is very, very close to 2. And what we discovered is that that number, the number we are approaching, is 5. So we just write equals 5. Don't write approximately equals. It's built into this that we're approaching. The number we are approaching, the number we're getting close to, is 5. And since f of x has a formula, we know we could also write it this way. Right? Sometimes we write these limits using the name of the function. Sometimes we write it using the formula. Okay, so with that in mind, let's look at these 4 examples. So for each one of these, I want you to first just stop and ask yourself, what does this mean? What does this each limit mean? If you understand the meaning of what you're trying to find, it'll be far easier. And feel free to use technology. You can use graphing, you can use a calculator to plug in numbers. Just wrap your head around what do these mean, and then use that as a tool to figure out your answer. Okay, so pause and actually try this. All right, so for this first one, the meaning here is if x is close to 1, what is 3x plus 5 close to? That's the question we want to answer. And just intuitively, you might be able to do this with no technology. Well, x is close to 1. Well, that's 3 times x. 3 times something close to 1, it's close to 3. Take a number close to 3 and add 5. I should be getting an answer that's close to 8. It just seems like if x is close to 1, this computation seems very straightforward, and I get an answer close to 8. We can confirm this with a graph. Right, here is our graph, if I can find it. If x is close to 1, y is close to 8. So this limit is equal to 8. Now this next example, it's saying if x is very, very close to 4, what is the approximate value of this fraction? And in this case, if you tried to do it just intuitively, you would be dividing by 0. So sometimes our intuition just gives us a meaningful answer right away. Sometimes we realize we're going to have to do something a little bit harder. But again, I'll just use graphing for all of these. So I have this example set up. If x is close to 4, right around here, if x is close to 4, I'm noticing y is close to 8. This is another graph that kind of looks like a line, technically has a hole in it, but we can barely tell. So this limit is equal to 8. Okay, let's look at this one. Same idea. If x is very close to 9, what is this function value very close to? So here's our graph. So here we go. If x is close to 9, I'm getting y values somewhere around 1.66. But in this case, it's not as simple as like, oh, I got this really nice number of 8, or I got this really nice number of 5. We might look at this and feel like maybe this is just an approximation. Right? How do I know if it's 1.663 or 1.664 or 1.668? It's really hard for us to tell that just from looking at the graph. We know we're getting answers around here, but technically speaking, there should be one perfect number. That of all the numbers around 1.66, there's one that we're getting super duper close to. So I want you to file this away. If we use a graph or we use numerical data, usually we can get in the right ballpark of what the limit is. But sometimes we might say like, oh, well, it's some kind of decimal, but I don't know exactly what it is. In cases like this, we will want to use other techniques so we can be 100% sure. I will tell you that the correct answer here will be a reasonably nice number. Some of you might recognize it, some of you might not recognize it. But there are numbers that are hard to recognize in decimal form. For example, the square root of 3, I think a lot of people wouldn't recognize that in decimal form. Pi divided by 6, I think a lot of people wouldn't recognize that in decimal form. So decimal form sometimes leads us astray, and we don't notice how nice the answer is. We will learn other ways to do limits. And this last one, bit of a doozy here. I have fractions within a fraction. I have this whole complicated thing. And I want to know what's the approximate value when t is very close to -2. And I will tell you, sometimes these limits are expressed in terms of different variables. Very often we'll be measuring things in terms of time. So calling our variable t makes a ton of sense. If you want to graph it, you're welcome to just switch everything to x. Whether we call the variable t or we call the variable x, it's the same pattern and the same answer. So for graphing purposes, if you want to change that to x, go ahead. And I've done this already. We want to know the approximate value when x is very close to -2. And here we go, right around here. Looks like if x is close to -2, y is close to -1. So this limit is -1. So this is the basic idea. A limit is just saying, what value are we very close to? There are cases where we plug in and we get something undefined, and that's when this is really useful to us. Yeah, technically it doesn't exist, but what is it supposed to be? Tell me what it's really close to. That's the idea of a limit. And in the rest of this section, we'll talk about better ways of computing them. But for now, I will stop.